Hi, welcome back to this video series on cryptography. In this segment, I will talk about how to find inverse of an element in a finite group. Our discussion is the inverse. For every element A in the group, we should be able to find another element called A inverse, right? Such that if you multiply, the answer should be 1 or identity element, okay? I'm going to use multiplication as a group operator in this segment. Now my goal is to show to you how to find an inverse of an element in a finite abelian group. Let's assume the group is G, right? G could be, for example, G star, say, let me use Z star 15. Okay, what is Z star 15? All elements that are relatively prime to 15 are part of this group. 1, 2, 4, 7, 8, 11, 13, and 14. So these are all the elements of Z star 15. We can see that under multiplication, this particular set forms an abelian group. For example, take 7 times 4. 7 times 4 is 28. 28 mod 15 is 13, which is present here. Okay. 1 is the identity element. Clearly, all elements, if you multiply with 1, you get the element back. And we can easily check that it's also commutative and associative. So we are talking about such a group in this discussion. Okay, so we are given a group G, which is assume an abelian group. Okay, now the question is, if I give you number 8 and ask you what is that you need to multiply 8 with to get 1 as answer. Okay, so we need to find essentially something equivalent to 1 by 8, which is 8 inverse in this set of elements. Okay, so I'm going to give you an algorithm. There are multiple interesting algorithms out there. I'm going to just give you one of the basic algorithms. Okay, so we are going to make use of this fascinating theorem. Suppose you have an element in your group. Let's say I call it element G in your group. Okay, it turned out that G power order of the group, let's say order of the group in this case, for example, how many elements are there? 3, 6, 8 elements. Order of the group means the number of elements. It turned out that G power order of the group is always 1. That's a spectacular result that we can leverage. Okay, we can check, for example, take 2. What is 2 power 8? 2 power 5 into 2 power 3, right? 2 power 5 itself is 32, which is nothing but 2 in mod 15. So it's nothing but 2 into 2 power 4, which is nothing but 1, right? 2 into 2 power 3, which is nothing but 2 power 4, which is nothing but 1. So the theorem we can verify for G being 2. Okay, you can try for yourself other examples and convince that G power order of the group is 1. Okay, I'll prove that in a minute, but we will take that and use this algorithm. You use this as a basis for our algorithm. So what if I rewrite this equation number 1 as follows? I just say rewrite this as G into G power minus 1. This is equal to 1, right? If you add the powers, you will get the same as the equation number 1. So which means this portion must be the inverse. That's all. So this must be the inverse of G. Okay, so we can very easily check now. So we wanted to find 8 inverse. It's nothing but 8 power 2 power 3 into 8, right? What is 8 power 2 is 64. 64 is nothing but 4 in mod 15. So 4 power 3. 4 power 3 is just 4, because 4 power 2 is 1 in mod 15. So we can just say 4 into 8, 32, which is nothing but 2. Okay, we can plug the number 2 here. We can confirm 8 into 2 is 16. 16 is nothing but 1 in mod 15. All right, so that's basically it. So given this theorem that says if you have an element G in your group, G power order of the group is 1, we can rewrite this equation as follows, and we can immediately convert this theorem into something that we can implement as an algorithm. All we need to know though is the order of the group. Okay, it turned out that this particular equation number 1 is a general version of Fermat's theorem. Okay, if you work with say for example Z star 5, 5 is a prime number. How many elements are there? It will be 1, 2, 3, 4, because all of the elements are relatively prime to 5. 1, 2, 3, 4. So order of the group in this case is 4. Okay. So Fermat's theorem says that if you have a prime number p, a power p minus 1 is nothing but 1 if p is prime. The converse need not be true. Okay. If p is prime, a power p minus 1 is congruent to 1 for all a less than p. Okay, in mod p. So obviously you can reduce a to a first, applying mod p. Okay, so this is the result of Fermat's theorem. And as you can see, p minus 1 is nothing but the order of the group. Whenever you have a group with, say, for example, z star p will have all the elements from 1 to p minus 1. Therefore, order of the group must be p minus 1 in this case, right? So this basically equation number 1 is a generalized version of Fermat's theorem, which is basically specialized only for z star p. Okay. As a matter of fact, Euler actually generalized Fermat's theorem into something called Euler's theorem. Euler is a celebrity. He has done amazing work, and one of the inventions is a power pi of n is equal to 1. This is invention of Euler. Okay, what is pi of n? Pi of n is the order of the group. In this case, for example, if n is 15, pi of n is 368. Okay, and as we have just verified, a power pi of n is equal to 1. This is Euler's theorem. Anyway, the equation number 1 is the much general version for all groups. If you have an element g power order of the group is 1, we can use that to create a program easily. Okay, which I'm going to show to you now. Let me show to you some simple example. Let's say we will leverage small groups, for example, z star 5. Okay, so let me show to you the z star 5 first. Z star 5 has elements 1, 2, 3, 4. Right. The way you need to read this table is as follows: 1 power 1 is 1, 2 power 1, 2 power 2, 2 power 3, 2 power 4 is 16, but everything is done in modify. Therefore, we can see 2 power 4 is actually 1. So the same with 3 power 1, 3 power 2 is 9, modify, 3 power 3, 3 power 4 is again 1. So as you can see, the last column is always 1. That's because of Fermat's theorem. Okay, we can also now try on non-prime elements. Okay, like for example 9. Okay, we can see here 2 power 5 is 32. 32 mod 9 is 5. 2 power 6 is 1. Okay, similarly 5 power 6 is also 1. Okay, as we can see, if you continue this sound for 1, again you write sound for 1. So I stop as soon as you get a 1. But if you fill up it again, you will see all the last columns, all the elements of the last column are actually 1. Okay, that is basically the theorem that I talked about. So with this background, we can do some very basic analysis. So let's say I want to find the mod inverse of generic version, right, for all groups, for the element, say 2. Okay, and the order of the group we know is 6, right, because z star 9 will have elements 1, 2, 4, 5, 7, and 8. Okay, so order of the group is 6, and we wanted to find out the modulus that we are working is 9. We want to find out the inverse of 2. Yeah, inverse of 2 is 5. We can check easily. 2 times 5 is 10, and 10 mod 9 is 1. That's exactly the definition of inverse. Just to be clear, I will write it. 2 times 5 is 1 in mod 9. Okay, that's what we just computed. Or the algorithm is essentially doing that part. Okay, it's computing this number 5 for us. It takes as input this number, and the order of the group must be known for the generic algorithm to work. But if you are thinking in terms of, say, just a regular prime instead of generic group, we can directly call Fermat's theorem. Let's go back to residue of some other number. Let's say residue of 7, right? Well, let's compute the inverse of 3. So what number would you multiply with 3 to get the answer to be 1? Okay, so we can do mod inverse Fermat. Okay, 3 in z star 7. So answer is 5. 3 times 5 is 15. 15 mod 7 is 1. As you can see, we can get a very easily, we can compute the inverse very easily using the theorem that I mentioned on the whiteboard. Okay. Okay, let's go back to the whiteboard and do a quick proof. Okay. So why is G is an element of a group? Why is G power, the order of the group is 1? Okay. I'm going to assume G is an abelian group. Okay. All right. So we select an element G. We will argue that G times G1 is one element from the group. Okay. And G times, this is G1, G times G2, we compute this. Let's assume the order of the group is M. Okay, there are M elements. So that means, what can we say about these sequence of products? We argue that each element here is distinct. The reason is that if they are equal, right, let's say G into Gi is equal to G into Gj for some I and j, distinct I and j. This means I and j must be equal according to the definition of the group. We can cancel G and G, Gi must be equal to Gj, but we assumed Ga is different from Gj. Okay, so all of these are distinct elements. And I also mentioned the order of the group is M. Okay, that means what we are doing essentially is just multiplying the elements of the group. That's what we are doing. Okay, so which is same as product of all the elements of the group, G1, G2, and Gm. Okay, so if the group is abelian, we can reorganize the brackets as follows. We can just say there's nothing but G power M, right, into G1, G2, and Gm. And again, we can divide both sides by G1, G2, Gm because it's the same value on both sides. This is allowed in a group. We can divide elements on both sides. So that means, okay, M is that means this whole thing will cancel out. So you will be left with 1 equal to G power M. That's exactly what we talked about. This is basically it. Okay. This is only possible if I assume G to be abelian group. Okay. This theorem is still true even if the group is not abelian. Okay, just a regular group, this is still true. G power order of group is 1. All right, that's basically it. So we presented a simple algorithm to compute an inverse of an element in a group. Thank you very much.